Hello everyone and welcome back to your YouTube channel and welcome to this video. This video is inside a series of videos talking about the performing time domain simulations using the DIgSILENT Power Factory, okay? And this video is a video where we will explain some basic features about this process, okay? In the previous video, I was discussing, explaining and giving some details about calculation methods. But it's time to go deeper and explain each one of those calculation methods, okay? And that is the plan for this short video. And here we have the balance RMS simulation, okay? This is probably the most used or typically used or entry function for people learning time domain simulations, okay, using the DIgSILENT Power Factory. Again, if you are using the new version of the DIgSILENT Power Factory, you will realize that the configuration in the initial condition calculation function has two options: simulation method and network representation. And in order to perform balanced RMS simulation, what we need to do is select first RMS values, and here in network representation select the positive sequence representation, and that is the representation used for balance system, okay? In this case, the balance RMS simulation, again, I will tell you, is probably the most used and the most basic, the entry level for time domain simulation. We call this time domain simulation because we get the response of the system based on the time. Time is the independent variable, and when we run the simulation, we get time series, okay? We get time series for each variable. For instance, here, as you can see, there is a plot, okay? The classical way to collect data from time domain simulation is using a plot. In that plot, we have a vertical axis where we can include several variables, and a horizontal axis that typically used for the representation of the independent variable time, okay? For instance, here, this is the representation of two voltages, and when you are running RMS simulation, remember that all the electrical variable, voltages, current, etc., they are characterized by the RMS values. What I am telling you is, for instance, in this plot, this voltage is a sine wave form because we are using AC system. We are working in a classical power system. Power system, they use AC signals. However, when we are using RMS simulation, we assume that the frequency is constant, equal to the fundamental frequency, and we can use the concept of RMS value. What I'm telling you here, this plot is representing the RMS value, but is representing the changes on the RMS value over the time, okay? For instance, here I can say, for instance, that this blue line here is representing the voltage, and the high voltage side, you can see over here, high voltage side, and we can say that is 1 per unit, okay? Suddenly we have a short circuit, the voltage go down, reach 0, there is no impedance, it's a solid or voltage short circuit, and then the short circuit is released. You can see some oscillations over here. But what you see over here is the RMS value of this voltage, okay? That is also the same if you are using currents or any other electrical variable. Now, as I said before, balanced RMS simulations, they are probably the most used kind of simulations. There are many applications where we need to use this. For instance, if we are interested on assessing the behavior of some kind of controllers, mechanical controllers, electrical controllers, and so on, well, we can use this kind of RMS simulation. That is valid, okay? And also, if we need to assess the performance of any energy system, for instance, a gas turbine or hydropower turbine, well, we can use this approach, okay? This approach is valid for this kind of application. For instance, if we want to see the reaction of the generator, the synchronous generator, and during a short circuit, We can use the RMS simulation, we can use the RMS values to do that. Or for instance, if we want to see how the system behaves, how the generation responds when we have a sudden load change, again, we can use this kind of simulation, the balanced RMS simulation. The balanced RMS simulations, they are quite straightforward in terms of the mathematical background because they are extremely simple, okay? The network representation, we are using the basic representation for the network. We assume that the network in a steady state can be represented by something that we call phasors. Voltages, currents, they are phasors, and the relationship between voltage and currents, they are expressed, or they are based using admittance matrix, for instance, okay? That is what I am trying to tell you. What I'm trying to tell you is that the network representation is extremely basic. In this case, we assume basic fundamental frequency moving through the whole system, and we can use phasor for voltage, for currents, and the relationship between voltage and currents is defined by the admittance matrix. Extremely simple, okay? It's extremely simple. In this case, we are using just positive sequence. Remember that. We are using just positive sequence because we are using balance consideration, okay? We assume that A, B, C, they are similar, they are equal, to be honest, identical, and we can use this approach, okay? And for the differential equations, is extremely simple because we will consider the dynamic of all the components. For instance, if we are talking about of the synchronous machine, we can use the classical swing equation. This is the swing equation you can see over here, and this is a first order differential equation. As I told you before, power factor is using the first derivative of the rotor speed to create the model of the synchronous machine, okay? We can do this, okay? We can do this, and that is extremely simple, extremely useful. What I'm trying to tell you is that in practical terms, from the mathematical point of view, the differential equation will define this set of differential equation here. And for instance, representing the network, we can use the admittance matrix, and we will consider this set of equations for the nonlinear algebraic equations, okay? And that is very simple. Okay, but this is the mathematical representation for the differential and algebraic equations, okay? Equations related with the dynamic, for instance, coming from the synchronous machine, but also algebraic equations coming from the network. However, there is a very important set of equations that we need to be careful, okay? When we are doing balanced RMS simulations, we have equations coming from the network, like here, okay? That we can use the positive sequence representation, the admittance matrix, and here we can use the most basic representation for the synchronous machine, the electromechanical model, the first differential equation defining the rotational speed, and so on. But remember something, there are different references, okay? The synchronous machine, there is a possibility of saliency, a rotor is salient pole, and we need to do something, okay? And that is translating the variable from the network to the machine, and from the machine to the network, okay? And that is where DQ0 transformation, Park transformation start to be important, okay? That is inside Power Factory, but Power Factory is including this kind of transformation inside to do the job for you, okay? But in this case, again, we have dynamic represented by differential equations here, for instance, the machines, and we have algebraic equations covering two sets. Differential equation coming from the transformation and algebraic equation coming from the transformation, and algebraic equations coming from the network, okay? Well, now it's time to extend the discussion to another type of time domain simulation in Power Factory, okay? Now we will keep using RMS simulation, but what we change is the network representation, okay? Imagine the case that we need to perform calculations. We are interested on short circuit, but we are working with an asymmetrical fault. For instance, line to neutral. line to neutral or line to ground, okay? This kind of asymmetrical conditions, you must remember, these asymmetrical conditions, they are extremely dangerous for the power system, and there is a mathematical tool to deal with this case. And the best way to deal with this case is using Fortescue theorem, Fortescue theory of symmetrical components, okay? Power Factory has the possibility of running this kind of time domain calculations. All the electrical quantities, they will be calculated using fundamental frequency, using representation based on RMS values, but the network can be represented again using admittance matrix, for instance, but in this case we can use positive, negative, and zero sequence, okay? What I'm telling you is that we are interested in this kind of simulation. We want to assess the performance of the system under this kind of asymmetrical conditions. Well, here you can see that positive, negative, and zero sequence, that is a possibility using fundamental frequency. And again, we can use dynamic equations to represent, differential equations to represent the components like synchronous machine, okay? The three-phase functionality inside Power Factory, in this case, use a steady-state RMS network model. That means that we can use this admittance or impedance matrix, okay? And this kind of studies, they are quite common, to be honest. Also, that is one of the classic mistakes of rookie users of Power Factory, that they try to use positive sequence to run the calculation for a single line fall. And then when they got a ground result, they start to scratch the head. If you are interested in asymmetrical condition, if you are using, for instance, a line-to-line short circuit, you need to select this three-phase RMS simulation. Okay, be careful with that. Please keep in mind. Okay. Basically, what you are doing inside Power Factory, in this case, where Power Factory is doing for you, is basically creating the three different sequence network representation: the positive sequence network, the negative sequence network, the zero sequence network, and then Power Factory internally, they are creating admittance or impedance matrix depending of the calculation, and then from there they can calculate all the asymmetrical variables, okay? This functionality is quite interesting, especially if you are trying to simulate events like single phase or two phase to ground short circuit, phase to phase short circuit, inter-circuit fault between different lines, or single or double phase line interruptions, okay? Something that is interesting, a lot of people, they are extremely familiar with short circuits, but then when we talk about serious fault, not much people are familiar with that, okay? Be careful with this. Be careful with this too, okay? In power system, there is a possibility that we have an open line or two open line, okay? One open line is probably most frequent than two lines, but that can happen, okay? A three-phase circuit breaker that doesn't open all the three poles, for instance, and then we establish a very asymmetrical condition, okay? That happened in the past, that is still happening. Modern power circuit breakers, they have a signal to be sure that all the three poles open or all the three poles close, okay? However, if we are dealing with old technology, that is not the case. For that reason, be careful. But what I want to tell you is that this kind of three-phase RMS simulation is quite useful, quite popular, okay? And also you can run symmetrical faults if you want, okay? However, if you run symmetrical faults using this approach, I must tell you that probably you are killing a fly with an atomic bomb, okay? Because you are overusing the tool for something that can be solved using positive sequence alone. Then we have here the three-phase EMT simulation, okay? As I said before, DIgSILENT Power Factory, inside there are two different configurations, the simulation method and the network representation, okay? When you are using RMS values for electromechanical transient, Power Factory allows you to select the network representation. However, when you are using instantaneous values, that option disappears, and it's clever. It's real, because if you are using instantaneous values, you need to use the full representation of the network. You need to use the unbalanced three-phase. Okay. And that is what is happening. Okay. Many people ask me, what is AMT? AMT is the initials of the electromagnetic transients. We are talking about that. In this case, we need the full representation of the components, okay? The full detail of the components. That means including all the resistance, capacitance, and inductances, but all the dynamics. I mean, the capacitors and the inductors, they will add differential equations for the model, okay? And this is one time domain simulation, and as I say before, in this AMT simulations, the results will be time series, but time series in instantaneous values. What I'm telling you, for instance, if you are plotting voltages, you will get the plot of the voltage, but the real instantaneous voltage. If you are using a AC system, the VA will be a sine wave representing the voltage on the line A, okay? This kind of simulation is quite useful, especially if we are working with over voltages or fast transient, okay? The typical application is basically where we need to take in account the interactions between capacitance and inductors. For instance, I say over voltages because over voltages is where you can see the most important interaction between magnetic field and electric field, okay? But there are several things that you can see. For instance, lightning strikes. Lightning strikes, they are one of the phenomena that you can find the use of these AMT simulations, of course, and also there are many others that you can see this, okay? For instance, if you are talking about over voltages created by switching, okay, in extra high voltage or ultra high voltage, opening a circuit breaker is a serious situation because you will excite some traveling waves inside the system, okay? It's very important that you take in account those over voltages when you are working with insulation, okay? Also, when we are using power converters, it's very important that we have a full detail of the short circuit current. And the best way to get the full representation of the short circuit current is using time domain simulation, specifically the three-phase AMT simulation. Also, some other phenomenons, interesting phenomenon like the inrush current or motor starting, it's quite useful to use this kind of AMT simulation. What is the bad news? Well, AMT simulation, they require very small time step for the integration, okay? It can be computational expensive. I mean, you will need a lot of resources from your computer because the time step is very small because you have so many differential equations with very, very small time constant, okay? And as I say before, in this kind of simulation, we use the three-phase representation, ABC, and full detail of everything, okay? We need the resistance, inductance, and capacitance of every single component, okay? The reality is this is used for very short time period, and the time step, as I say, is quite small. The interesting thing is that every single component that every single component that has some kind of dynamics must be included. For instance, the resistor has not dynamics. The resistor is just basically a linear component. In this kind of linear component, the voltage is equal to the resistance multiplied by the current, okay? But the capacitor and the inductor will be represented by the inductance and the capacitance, okay? In this case, we are using differential equation for the inductor. We are using integral equation for the capacitor, okay? Well, as you can see, inductance and reactance, they are fully explicit include in the dynamic. And as you must be aware, the inductance and the capacitance in the electrical power system, they are usually very low. And that is the reason that the dynamic involved in this case is extremely, extremely fast, okay? And it's related with the energy interchange between those inductors and capacitors. And that is the reason for the name electromagnetic transient, okay? The representation, the representation for the three-phase EMT simulation, it's look extremely simple, but it's not like that, because at the end, the differential equations used, it will be a set of first-order differential equation, and in that case, we need to include that differential equation into the whole set of the differential algebraic model, okay? It's quite interesting because the resistor will include it will have influence on the algebraic side of the equation, and the capacitors and the inductors, they will include terms on the dynamic, I mean differential or integral equation, okay? One of the main characteristics of the three-phase EMT simulation is that they are extremely slower compared with the RMS simulation, and that is because for the same simulation time, the EMT simulation need to use a smaller time step, and that is the reason that the EMT used to be slower than the AMT, than the RMS simulation, okay? The integration step is much smaller, and as a consequence, calculation time is a bit higher compared with the RMS. The good news is the DIgSILENT power factory is equipped with a very good set of solvers, and it's able to solve this three-phase AMT simulation in a proper way. And in this case, also, the DIgSILENT power factory is including what we call the variable step size with automatic step size adaptation, okay? What does it mean? Well, it's something very simple to explain, very hard to see from the mathematical point of view. Typically, we explain in classes for power system analysis that when we integrate the differential equation, we use a time step. But typically in master classes, we use what we call constant time step, because we take the time. The time is a continuous variable, and that variable is discrete size. And when we create a discrete space for the time, in that cases we are selecting several points, okay? When we say constant time step, it's because the separation, the distance in time between two different points is the same. It's constant. However, DIgSILENT power factory has some numerical routines that they allow that depending on the complexity of the dynamic, the time step can be increased or decreased. And that is a very important point. That is a very valid point, because when we are using AMT simulations, using constant time step is very time consuming. But if the fast transients, they decrease and they disappear fast, well, DIgSILENT has the possibility of understanding that the fast transient has already stopped, and they can increase the time step in order to speed up the simulation, okay? There are much more to explain about variable step size, okay? That is a very good mathematical aspect. Not much people expert on that topic, but it's extremely important, especially if you are creating commercial software, okay? Another thing that I almost forget to say is that three-phase EMT simulation is typically the simulation used by real-time simulators, okay? Real-time simulators, they are different to the simulation offline that we are talking about here, but later in the in the semester, I will be discussing about real-time simulators, and you will understand that those real-time simulators, they can run really fast simulation, EMT simulation, because they use a different type of hardware, okay? The hardware is extremely important when you are defining the speed of your simulations, but that is a topic that we will discuss in another video, okay?